All right. So basically, this is what we have already covered. Like I said, we did variable separable, right? We did variable separable, and I said homogeneous first order is already there on the YouTube. I've already did the videos on homogeneous. So I'm jumping to the linear first order differential equations. Okay, that's what we are actually going to do. And do not forget, I said all of these, number 1 to number 6, all of these are the techniques that we use to actually integrate to do what? To determine the general solution. It could be general solution. It could be particular solution. It depends on what will be given to you. And then after, we're gonna jump to Bernoulli. Now, let us discuss before we solve the questions under linear first order differential equations, right? We're going to discuss what are linear first order differential equations. How do you tell that these are linear first order differential equations? Okay, because like I said, these things, they can be really confusing. In exam, they're not going to tell you which technique to use to integrate this. You should be able to see these things by yourselves. So we're going to start looking at the basics that are going to help us actually to spot out these different types of techniques when it comes to solving different types of equations. So now, again, we need to understand the standard form. How does a linear equation look like? There are certain rules that are assigned to differentiate this type of equations. Remember, we know that we have the differential equations, but what are the linear first order differential equations? We have already started with differential equations, right? So when you talk about the linear first order differential equations, we are talking about the equations. Let me make an example, okay? Let me give you an example. Let's start with an example. Say, for example, you have a differential equation that look like this. Let's say we have dy dx is actually equals to, oh, okay, let me do it like this. I want to do it like this already. Let me erase everything and then go back to my pen. Whoop. Go back to my pen. So example of a linear first order differential equation, it's an equation that looks like this. Say we have dy divided by the dx, let's say plus 5y is equals to, let's say, e to the power of 2x, right? This is a differential equation because it has derivative. That's what we have learned. But this type of differential equation, is it linear or is it non-linear? Now, like I said, there are certain rules that we need to take into consideration when concluding whether it is linear or non-linear. But now, what are those rules? Now, for a function, for a differential equation, for a differential equation to be a linear, what are we going to look at? We're going to focus on the dependent and independent variable. We are also going to focus on the derivative of the function. Here's the first rule, okay? Number one, order of the differential equation should be 1. We have learned the degree of the equations. We have learned the orders of the equations. Now, what is the degree of this differential equation? Degree of this differential equation is going to be 1 because we can see that this dy over dx, it is actually raised to the power of 1. But if you have dy over dx to the power of 2, the degree of this is equals to 2. Now, let's talk about the order. Now, the order, we're going to look at how many times was this equation actually derived. This equation was derived only once. We can see that we have d1, dy, d to the power of 1, y, multiplied by dx, 1. But if you have d squared multiplied by 1 to dx squared, now what is the order of this differential equation that has derivative that looks like this? We're going to say the order of this is going to be 2. So the moment when the equation has a second order, we won't consider it as a linear first order differential equation. We need first order, see first order. So here we have first order because we can see that we have 1 and then to the power of x when you have 1. Therefore, this helps this equation to be linear. But we're not only looking at that. What also do we check to see whether this equation is linear or not? The other thing that we check is the dependent variable should have exponent 1 all the times. In this case, why it is dependent? Because remember, if I were to draw, remember from your basics, if I have to draw a Cartesian plane, y-axis, and then here we have x-axis. So what I change over here will affect everything on this side. So meaning x, it is independent because I change the values of x, and then I measure or I read the values of y. So y depends on x. So we say y, it is dependent, right? Because it depends on x, and then we say x, it is independent. It depends on itself. So in this case, when you are given your differential equation in this form, you have to understand that dy over dx, the one that we see at the top, and you have to be careful because sometimes it could be vice versa. X, you see this x, it is independent, right? X sometimes can be dependent and y can be in. So you need to be careful when it comes to things like this. But now in this case, we can see that because dy is at the top, dx it is at the bottom. So that means y, it is dependent. X, it is independent. But if it was like this, dx over dy, it is possible, it can happen, okay? So if it was like this, therefore x, it will be our dependent, y will be independent. If it's like this, just be careful when you are deriving in respect to y. But here we are deriving in respect to x. So the dependent variable should have exponent 1, which is y. In this case, our dependent variable, it is y. Look at the dependent, the exponent should be 1 all the times. The moment if here we had 2, therefore that will be non-linear. I don't care what's happening here. So we need to check all of those rules, okay? If those rules are, but if one rule fail, therefore the equation becomes non-linear. But if all of the rules hold, that means the equation becomes linear, okay? So if here we have 2, it's non-linear, but because we have 1, therefore it is a linear differential equation. And then another thing that we look at, it is the value of, you will see why I say Q. I'll explain to you that this value over here, we say it's Q, okay? So Q should be a function of independent variable. In this case, our independent variable, remember, it's X. So Q, it is the function of independent variable, or Q can be constant. If our equation was like this, dy over dx plus 5y is equals to e to the power of 2x multiplied by y. Will this be will be this a linear or non-linear? Number one, this will most definitely be a non-linear, right? Why? Because you have to be careful because at some point you can divide, you can multiply, you can do all of those things, okay? Now this is what is happening. Sometimes you need to understand that the coefficient of dy, dx should be 1 so that this can be linear. Meaning, if we had y over there, whatever, and then we divide, sometimes you can have y and then you divide the whole thing and then the equation changes. I can maybe, let's say we have dy over dx and say here we multiply by y. It's non-linear. But when we divide by this y, we get rid of this y and then we start to solve or simplify our equation, it will turn into a linear. So we need to be careful. But now in this case, having a look at this, our value of q is actually multiplied with the dependent variable. Therefore, this will be non-linear. So this equation to be linear, we're not supposed to multiply our q with the dependent. Our q is supposed to have the independent, in this case, which is x. So it's non-linear when it's like this. Again, when the equation is like this, say 5y, and then here we have, let's say we have 3. This is a linear, okay? So our value of q over here, it's either it's a constant or it is a independent variable, and therefore this will be a linear equation. Okay, so these are the most important things that we need to take into consideration, because when you want to integrate, you need to understand, am I seeing linear equation or not? But because if it is not a linear equation, then we're going to have a problem. We won't be able to use this technique to integrate our differential equation to get the general or particular solution. Now this is what we need to do right now. Okay, when you talk about the differential equation, this is a standard form of a linear equation. Let's write the standard form of a linear equation. The standard form of a linear equation, this is how we're supposed to look at the linear equation. We have dy dx plus py is equals to q. This is a linear standard form. Okay, this is a standard form of a linear equation. When you have an equation like this, you can easily integrate it, but you will see how. In this case, when you have this standard form, we have what you call the integration factor. Okay, having integration factor, we can denote our integration factor as r, or you can say I r. It's fine. That does not matter how you want to call it, but our integration factor will just denote it as r. Okay, so in this case, our integration factor will be e to the power of integral of p dx, right? This will be our integration factor, and therefore here we have the value of q. So to determine the integration factor, we use the coefficient of our dependent variable, in this case, which is p. We're going to substitute p over there. Okay, and therefore after integrating this, and then after determining the integration factor and knowing the value of q, I'm not gonna go too much on the details because I just wanna let you guys to learn how to solve these things. Okay, I'm not gonna waste much time to show you or to prove 1, 2, 3. So when you are on this part, the second thing that you need to do is you're gonna take your dependent variable, which is y, you multiply it with your integration factor, you equate it to the integral of your what? Of your integration factor, multiply by the value of q dy. Why am I saying dy? Because my y, it is my dependent variable. Like I said, this dependent and independent variable, they can change. So you really need to be careful. So now, this is how we're going to solve the linear first order differential equation. Okay, this is a standard form. This is the integration factor. And then this is how we go to the final answer. If you are given the differential equation, this will help you to determine the general solution of your differential equation. So these are the only things that you need. Now let's go through the examples. Now we have a question, right? Which is denoted by dy over dx is equals to x1 minus 2y. Now the question is, which technique am I going to use to determine the general solution of this equation? We need to determine the general solution of this equation. We did separable variable, right? Will that work? It won't work. That's you me. Let me show you how am I saying it won't work. Remember, we said this will be divided by 1. And then you're going to say 1 multiplied by dy, it's going to be dy. And then you're going to say dx multiplied by that. You're going to say you have x 1 subtract 2y dx. Even if you divide by x, you're going to have 1 over x dy is equals to 1 subtract 2y dx. Apparently can work. And now I see how can it work. But remember, here it's x and dy. It's wrong like this, right? So the best way to do it is when we divide by 1 over 2x. So if we divide by x, it's going to be absolutely wrong. Therefore, separable variable, it seems impossible. But from here, and then we divide by 1 minus 2y. So that means when we divide by 1 y minus 2y, this side we're going to have 1 over 1 minus 2y multiplied by dy, and then this side we're going to leave x, we're going to have x dx. Still separable could work. So here's the challenge. What I'm going to do is, because linear can also work in this case, okay, linear can also work. So remember, it does not matter which technique works, as long as you know all of these techniques and be able to spot all of these techniques, if whether they work or not. Apparently, separable can also work. Use separable and see if you're gonna get the same answer if I use the linear method, okay? But let's see if it's linear, okay? Let's see, because you can see separable can work. Then let's see if linear can work. Now remember, we need this standard form. This is what we need. dy over dx plus py is equals to q. We need to make this equation to look like something like that, right? So now let us start. So we're going to distribute x inside of the bracket. So here we're going to have dy over dx. Dx is equals to x multiplied by 1. It will be x. This multiplied by that, it will be negative 2xy, right? And then look, we want dy over dx on this side. It is fine. So let's leave it at this side of the equation. And therefore, we want to take the dependent variable because dy, it is our dependent variable. We're going to take this guy on the other side of the equation. It's going to be positive 2xy, and then is equals to x, which is this guy over there. Now we wrote it in this standard form. Let's confirm if this is linear or not. Remember, our y independent, our dependent variable should be exponent of 1, correct? Our order of dy over dx should be 1, correct? And then our q, it should be the independent variable, not the dependent variable, correct? So it does not matter what you multiply your y with. Even if you multiply with the independent, it is still correct. It is still a linear equation, okay? So now let's talk. Are we going to be able to differentiate what we have y? We have y, our p will be 2x, our q will be x. We are happy. Now we can see that the linear first order differential equation is working. Separable variable, it is also working. So either way, whatever any method that you want to do, be comfortable with it, do it, it's fine. What matters is you get to the final answer. Now let's try this then. So our p in this case, is going to be the coefficient of our dependent variable, which is 2x, right? We agree. And then our q in this case is going to be this independent or constant. If it was a constant, it was still going to be fine. But in this case, it is independent. 1 multiplied by independent variable, it is still correct. So our q in this case is going to be x. Now, applying all of the basics that I have already spoke about, I said to you that we have what you call the integration factor, right? Integration factor depends on the value of p, which is the coefficient of the dependent variable. So that means our integration factor, we denote our integration factor as r. So meaning in this case, our r is going to be e to the exponent of integral of p dx, right? Now let us substitute e to the integral of p in this case is going to be 2x dx, right? So if our dependent, if our independent variable was t, we were going to write p dt. So we just write in p dx because our independent variable, it is x. But if our independent variable here was z or z, you're going to write integral of p dz or that z. So be careful, be extremely careful. So here we have e to the power of integral of 2x dx, right? So let us integrate this. I understand this is indefinite integral, but you don't have to write c. So integrating this, we have e to the power of, we take 2 outside, and then we're going to have x squared. So when you integrate 2x, we know that we're going to add 1 to 1 is going to be 2. We divide by 1 over 2 is going to cancel this 2, and then answer will be x squared. So integrating this exponent, answer will be x squared. Now our integration factor will be equals to that. We are done. Now the value of q is equals to that. The value of q is equals to x. Now where do we go? Now we go here. Remember, what did we say? We said that we're going to say our dependent variable, which is y, multiplied by the integration factor, is equals to the integral of the integration factor multiplied by q, and then our independent variable is x. Therefore, we're going to have dx over there. Right? Now, after having this, we substitute. So we have y as our y, and then our integration factor is going to be e to the power of x squared, which will be equals to Our integration factor once more again is going to be e to the power of x squared multiplied by q. Q in this case is going to be x, right? Dx. Now, from here now we integrate, because remember, we have a differential equation. We want to determine the general solution. It's all about integrating, but integrating in which using which technique. So now we integrated it. So now let us integrate this part. So trying to integrate this part by just looking at this is simple, guys. I know some of you, you see, within integrating technique, you apply other integrating technique. Like here, I understand it's linear differential equations, but we're going to apply by parts, or you can apply U substitution or partial, whatever that you apply, it is still fine. So in this case, to integrate this, I can see that we can apply U substitution. Look at this. How do I see that I can apply U substitution? It's simple, because I have x to the power of 2, and then I have x. Each and every time when you have your variable like this, the other one, it is raised to the power of 2, the other one is just that. So I'm going to let x to the power of 2, the one that has the higher degree, I'm going to let it to be equals to u, okay? So on this side of the equation, let us try to integrate this side, which is integral of ex to the power of 2 multiplied by x dx. So what I'm going to do is I'm going to let me change my color here. I'm actually going to look, I am going to let u to be equals to x squared. And then the very same equation, I'm going to differentiate it. So I'm going to have du divided by dx is equals to, we know that we're going to have 2x differentiating, right? So that we see after differentiating x squared, now I have x. So this x will cancel with that x. That's the reason why I say my u is x to the power of 2. Now from here, this is what I'm going to do. I'm going to make dx subject of the formula. But how am I going to do that? I'm going to have dx over du is equals to, I take the reciprocal on both sides of the equation, and then I cross multiply, blah, 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 however you want to do it. And I see that my dx will be is going to be equals to, 1 over 2x du. Okay. Now, I'm going to substitute that. Okay, let me change my color. Substitute. So here we have the integral of e. We said x squared, it is u, right? And then multiply by x. And then we say the dx, that is 1 over 2x du. And therefore, we have the integral of e to the power of u. This x will cancel that x, and therefore we have multiplied by 1 over 2 du. Now let us integrate this. I take 1 over 2 as a constant. Outside of the integral sign, I have e to the power of u du. Now let us integrate this. 1 over 2, what is e to the power of u? It's going to be e to the power of u plus c. Now you see this side, which is this. We're going to say y multiplied by e x to the power of u is equals to this, which is 1 over 2 e to the power of u plus c. But remember, we said that u is actually equals to x squared plus c. Actually, this will be our final answer, but again, it depends on the statement, okay? If the question said, determine the general solution of this differential equation and leave your answer in explicit form. They can say in explicit form, or it can be in implicit form. So when the answer, it is actually in implicit form, in implicit form. So that means this is where we are actually going to leave our answer. But now, if we want to leave it in explicit form, so that means we're gonna have to do what? We're gonna have to make y the subject of the formula. Okay, we're gonna have to do y the subject of the formula. So now that means we're gonna say y.
Can you repeat that statement you said like 2 minutes ago?
Which statement?
No, the one where we have to make y the subject of the formula.